Okay, we're back here looking at rotational kinematics. This is for objects that are rotating, and unlike before where they were at a constant angular velocity, these objects could be speeding up or slowing down. So think about you're sitting in your house and you turn a light switch up so that your ceiling fan now starts to spin. It doesn't immediately start spinning at the speed that's max speed. It slowly starts to speed up. It's accelerating. And whenever you turn that light switch off, it slowly begins to slow down. Because of this, we have an acceleration or a deceleration here, a negative acceleration to think about it like that. And because of this, we cannot use equation 1r from our best friend sheet. We are stuck using these following four equations: 2r, 3r, 4r, and 5r. These equations here allow us to incorporate an acceleration. And because we have an acceleration here, the ceiling fan speeding up or speeding down, we are stuck to use these equations. We can't use anything else here. But the same things we did early on in this year when we were talking about free-falling objects and how Earth's gravitation, gravitational acceleration is causing objects to speed up or slow down. We're doing the same exact thing here with these equations. Nothing has changed. In all cases, we are trying to just identify which of the quantities we know and then just pick an equation which only has those quantities and the one we're looking for. And pretty much, if you remember this, if you have 3 out of the 5 quantities that exist, you can go and find the fourth unknown. So our 5 quantities we have are an initial angular acceleration, a final angular acceleration, initial and final angular velocities, an angular acceleration, a time, or an angular distance. If you have 3 of them, 1, 2, 3, you can go and get an acceleration somewhere else. You just need to choose the right equation. Okay? So what we're going to do is we're going to look at a ceiling fan problem here. And what we have is we have a ceiling fan blade, and it is turning initially at 8.5 radians per second at a low speed. We then switch it from a low to a high setting. So we pull the little cord there. It takes 3.2 seconds, some amount of time, to reach the high speed of 15.4 radians per second. So we just want to label this real quick. We can call this an initial angular speed. This is our final angular speed or angular velocity. And this is a time. So what's the angular acceleration of the fan blade? Well, lucky for us, we've got 1, 2, 3 things here. We just need to choose the right equation that gives us angular acceleration, which is alpha. If we go up and take a look at our equations here, I need to look at an equation that has a omega I, omega f, a t, and an a. And if we're looking at these and you're looking at your sheet, the one that pops out is this first one here. Whenever we go to solve this, we can say that our alpha, our angular acceleration, that's just equal to a final angular velocity minus an initial angular velocity divided by some amount of time. At this point, we just have to plug in numbers, and the problem kind of solves itself. We've got 15.4 radians per second for our final minus 8.5 radians per second for our initial. And then we just divide that by the 3.2, making sure we do the numerator subtraction before that division for the denominator. If we run this, let's pull out a calculator. 15.4 minus 8.5 gives me 6.9 divided by 3.2. I get 2.15, let's just round up to 1.6 radians per second. And remember, this is actually radians per second per second. So this is like radians per second squared. Just like we saw with accelerations earlier on this year, were meters per second squared. These are radians per second squared for accelerations. If we want to know what the blade's angular displacement was during this acceleration, well, we're looking for theta then. And what we have is pretty much everything else. We have a final velocity, we've got initials, we've got time, we've got alphas. We just need to find an equation that has theta in it. So we could use this last equation, but I actually like this equation right here because it's already in terms of theta. So let's go ahead and use it. We can say that the initial angular velocity times the amount of time plus 1/2 alpha t squared, that's a half. And just throwing in numbers, we've got 8.5 radians per second times the 3.2 seconds. That gives us radians there, which is nice. That's what our angle is. It's in radians. And then that's plus 1/2 of 2.16 radians per second squared. And this works well because whenever we have 3.2 seconds here, that quantity is squared and our seconds go away, which means that we're left with just radians. 8.5 times 3.2 is 27.2 here. Radians plus, don't forget we have to square that 3.2. So 3.2 squared times 2.16 divided by 2 for the half. That gives us an additional 11, well, let's just leave it at 11 radians. And that means when we add them together, our final answer is going to be something on the order, oops, did I say 27 there? I meant 27. Our final answer is going to be on the order of 38.2 radians. If we wanted to put that in terms of pies, then if we divided the 38.2 divided by pi, then we could actually also say that this is equal to about 12.16 pi radians. And that's that final answer there. Okay, so both ways we'll do that as well. But right there, it's basically just kinematics that we did earlier this year. We're just using some slightly stylized equations in order to do it. If we have 3 of our 5 components, we can find the 4th. It's just a matter of looking at the equations and seeing what you got. So take a look at some of those problems from the first homework set, the 3 of them there. You should be able to do them all. If you've got any questions, please ask for some help. Shoot me an email. Catch me during office hours. And check out the next video. Take it easy.